Matter exists in three states: solid, liquid, and gas, and we use the kinetic model of matter to describe the properties of the three states. So in a solid, we say that the particles are in fixed positions. Here, particles in this chapter will mean atoms and molecules. Atoms and molecules will be referred to as particles. So in a solid, the particles are in fixed positions. They can only vibrate about the fixed position because there are strong forces holding the particles together. And that's why a solid has a definite volume and a definite shape. In a liquid, the particles are further apart than in a solid. This is because the forces between particles in a liquid are weaker than in a solid. Thus, the particles can move throughout the liquid. That's why a liquid has no definite shape. A liquid will take the shape of the container. But the forces between the particles are still significant, so that the liquid has a definite volume. The particles stay together. In a gas, the forces between the particles are very weak and can be considered negligible. So the gas particles can move around freely. So a gas has no definite shape and no definite volume. It will completely fill its container. A solid can change to a liquid by a process called melting, or a liquid can change to a solid by a process called freezing. So melting is a process whereby a solid changes to a liquid without any change in temperature. And freezing is a process whereby a liquid changes to a solid without any change in temperature. It's important to mention that the two processes occur without any change in temperature. Now, melting and freezing occurs at the same temperature for a substance. For example, pure water, when cooled, will freeze at 0 degrees to become ice. And pure ice, when heated, will melt at 0 degrees. So the freezing point and the melting point is the same. Now suppose you have a piece of ice at -5 degrees Celsius, and then we heat the ice. The temperature of the ice will increase until it reaches 0 degrees, and then it starts to melt. And during melting, temperature will stay constant. So the temperature increases until it reaches its melting point, and then when it melts, temperature doesn't change. So the ice at 0 degrees will melt completely to water at 0 degrees, and then the temperature of the water will increase. So during the melting process, temperature remains constant. So why is temperature constant during melting? But to explain this, we use the kinetic model of matter. And according to this model, the particles in a solid, liquid, or gas are always in motion. So here is a solid, and when the body is heated, the heat energy it absorbs is converted to the Ki of the body's particles, and the particles move faster. So when you heat a solid, the heat energy is converted to kinetic energy of the particles, and they move faster. So here we have a solid, and here we have the same solid at a higher temperature. And you can see that the particles are vibrating faster and with greater amplitude. So when the particles absorb heat energy, their kinetic energy increases, and that's when we say their temperature has increased. And the same thing applies for liquids and gases. The higher the temperature, the faster the particles move. Here we have a liquid, and here we have the same liquid at a higher temperature. The particles are moving faster. And here is a gas, and here's the same gas at a higher temperature. The particles are moving faster, they have more kinetic energy. So here temperature is higher. So temperature is a measure of the kinetic energy of the particles in a body. Now when we look at a solid, So what happens to the solid when it is heated? The particles gain energy, they move faster, and at a certain point they can have enough energy to break the bonds between them. And then they move apart from each other and the solid turns into a liquid. So at the melting point, the particles have enough energy to move apart from each other and the solid melts to a liquid. As they move apart, the particles' electrical potential energy increases and not their kinetic energy. And hence, we say that the solid's temperature does not increase during melting. This is because during melting, it's the potential energy of the particles, the electrical potential energy, that increases and not kinetic energy. And since temperature is related to kinetic energy of the particles, so during melting, temperature does not increase. So for example, here we have a piece of ice at -5 degrees Celsius. When you heat the ice, the particles in the ice move faster, so its temperature increases. But at 0 degrees, it starts to melt. The particles have enough energy now to move apart from each other. So the ice will turn to a liquid. And as the particles move apart from each other, their potential energy increases. So during melting, temperature will remain constant because the potential energy of the particles increases and not the kinetic energy. So the ice will melt completely to water at 0 degrees Celsius, no change in temperature. And then if we heat it further, now the particles will move faster, their kinetic energy will increase, and its temperature will increase. Now the same thing applies for freezing. So temperature will remain constant during freezing for the same reason. Suppose you have water at 10 degrees Celsius and you remove heat from the water. So you remove energy, the particles will lose kinetic energy, they will move less fast, they will be more slowly moving. So their kinetic energy decreases. And since temperature is related to kinetic energy, as the kinetic energy decreases, the temperature decreases. And then at 0 degrees, the particles start forming bonds so that the liquid turns to a solid. So the liquid freezes to a solid. And as the particles form bonds, they become closer together, their potential energy decreases and not kinetic energy. So during freezing, the temperature will remain constant since potential energy of particles decreases and not kinetic energy. So the water will freeze to ice at 0 degrees, and during the freezing process, it's P that decreases and not K. So temperature remains constant. And then when all the water has turned to ice at 0 degrees, you keep cooling it. Now the particles will lose kinetic energy and the temperature will decrease. So that's why temperature remains constant during freezing and melting. The specific heat capacity C of a substance is the amount of heat energy, also called thermal energy, required to raise the temperature of the body by 1 Kelvin or 1 degree Celsius. So this is a definition for specific heat capacity. Note that a change in temperature of 1 Kelvin is the same as a change in temperature of 1 degree Celsius. For example, on the Kelvin scale, 0 Kelvin is equivalent to minus 273.15 degrees Celsius. So the values are not the same. But the scale has been made such that an increase in 1 Kelvin is the same as an increase in 1 degree Celsius. So 1 Kelvin is equivalent to minus 272.15 degrees Celsius. Both has increased by 1 degree. Another example, 0 degrees is equivalent to 273.15 Kelvin. So if a change in 1 degree Celsius will be equivalent to a change in 1 Kelvin. So 1 degree Celsius is 274.15 Kelvin. Both has increased by 1 degree Celsius. So a change in 1 Kelvin is the same as a change in 1 degree Celsius. So looking at the definition again, the specific heat capacity C of a substance is the amount of heat energy required to raise the temperature of 1 kilogram of the body by 1 Kelvin or 1 degree Celsius. And the formula to calculate specific heat capacity is C is equal to Q over M delta theta, where Q is the energy supplied or removed in joules, C is the specific heat capacity, and delta theta is the change in temperature in Kelvin, and M is the mass in kilograms. You can rearrange this formula to get Q, energy Q, is equal to mc delta theta. Now an example, a body has a mass of 2 kilograms. Its temperature rises from 10 degrees Celsius to 100 degrees Celsius when 216,000 joules of heat is supplied to it. Calculate its specific heat capacity. So we are given the energy supplied Q is 216,000. The mass is 2 kilograms. Change in temperature is 100 degrees Celsius minus 10. That's 90 degrees Celsius, and this is the same as 90 Kelvin. A change in 90 degrees Celsius is the same as a change of 90 Kelvin. So we replace the values in the formula, and we have Q is equal to 216,000, mass is 2 kilograms, and change in temperature is 90 Kelvin. And the specific heat capacity is 1200 joules per kilogram Kelvin. Note the unit for specific heat capacity, joule per kilogram per Kelvin. Example 2, a body has a mass of 3 kilograms. Its temperature decreases from 10 to 0 degrees Celsius when it loses 9,000 joule of heat energy. Calculate its specific heat capacity. So energy removed is 9,000 joule. Its mass is 3 kilograms. Change in temperature is 10 degrees Celsius minus 0 degrees Celsius. That's 10 degrees Celsius, and it's equivalent to 10 Kelvin. So whether it is heated or it is cooled, we use the same formula. So here Q is energy removed, not energy supplied. So energy removed is 9,000 joule, and mass and delta theta we replace their values, and we have 300 joule per kilogram Kelvin as the specific heat capacity. Example 3, water has a specific heat capacity of 4,200 joules per kilogram Kelvin. How much thermal energy is required to increase the temperature of 4 kilograms of water by 60 Kelvin? So we are looking for energy supplied, Q. Mass is given, 4 kilograms. Change in temperature is 60 Kelvin, and specific heat capacity is 4,200. And then we use formula Q is equal to mc delta theta. Replace the values. M is 4 kilograms, C is 4,200, change in temperature is 60, and we have 1,008,000 joules of heat energy. This is the amount of heat required to increase the temperature of 4 kilograms of water by 60 Kelvin or 60 degrees Celsius. A mass of 0.3 kilograms of water at 95 degrees Celsius is mixed with 0.5 kilograms of water at 20 degrees Celsius. Calculate the final temperature of the water given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. So when we mix water at different temperatures, so you have a sample of water at 95 degrees Celsius, and you mix it with water at 20 degrees Celsius. So the final mixture will have a temperature that is between 95 degrees and 20 degrees Celsius. So we say that T be the final temperature of the mixture. So you have 0.3 kilograms of water at 95 degrees Celsius, and we are going to add 0.5 kilograms of water at 20 degrees Celsius. So heat will flow from the warmer sample 95 degrees Celsius, and heat will flow to the water at 20 degrees Celsius, and temperature of this sample will decrease and temperature of this sample will increase. So the final temperature is between 95 and 20, so we call it T. Now the temperature change for this sample will be 95 degrees minus T, since the temperature decreases from 95 to T. And this sample, the temperature change will be T minus 20 degrees Celsius, since its temperature increases from 20 to T. And the energy lost by the hot water is the energy gained by the cold water. So heat energy lost by the hot water is heat energy gained by the cold water. To calculate energy, we use mc delta theta. So for this sample, m is 0.3 kilograms, c is 4200, it is water, and change temperature is 95 degrees Celsius minus T. And for the second sample, m is 0.5 kilogram, c is 4200, it is water again, and delta theta is T minus 20 degrees Celsius. So replace these values. So m is 0.3, c is 4200, 95 minus T, change in temperature. Here mass is 0.5, c is 4200, and T minus 20 is change in temperature. And we solve, we have T is equal to 48 degrees Celsius. So to find the specific heat capacity of a solid or liquid, we measure the mass m of the solid or liquid. We heat the solid or liquid and note the temperature change delta theta. We calculate the heat energy Q supplied to the solid or liquid, and then we use the equation C is equal to Q over m delta theta. So in this example, we find the specific heat capacity of a metal block using an electrical method. And the apparatus used is called a calorimeter. A calorimeter consists of a container which has lagging. Lagging is simply an insulator placed around the container that prevents heat from escaping from the solid or prevents heat from entering from the surrounding into the solid. So lagging is insulation around the container to minimize heat transfer. The metal block is placed inside the calorimeter. Holes are drilled in the metal block. So a heater is placed in one of the holes and a thermometer is placed in the second hole. The heater is connected to a power supply. An ammeter measures the current through the heater, and a voltmeter measures the voltage across the heater. Now we heat the solid for a time t. Power supplied to the heater is voltage times current. So energy supplied Q is power multiplied by time. So power is VI and time is T. We measure with a stopwatch. So energy supplied is VIT. We measure the mass m of the block on a balance. When timing is started, we note the initial temperature, and when we stop timing, we note the final temperature, and we calculate delta theta, the change in temperature. And then using C is equal to Q over m delta theta. Q is VIT. M and delta theta, we replace the values and we have the specific heat capacity of the solid. However, in this example, we have assumed that heat is not absorbed or lost to the surroundings. Now, in practice, there is always some heat that is absorbed or lost to the surroundings despite there is lagging around the container. So we need to take into account the heat lost or absorbed to the surroundings. So how do we account for heat losses to the surroundings? So first, we cool the metal block until its temperature is below room temperature by a certain amount. For example, suppose room temperature is 22 degrees Celsius. We cool the block 10 degrees below room temperature. So we cool the block to 12 degrees Celsius. That's 10 degrees below room temperature. Next, we heat the metal block until its temperature is above room temperature by the same amount. So we will heat the metal block until its temperature is above room temperature by 10 degrees. So we will heat it to 32 degrees. So we started 10 degrees below room temperature and we're going to heat it 10 degrees above room temperature. Now when it is colder than room temperature, heat will move from the surrounding air into the block because the air is warmer than the block. When we heat it, when its temperature is equal to room temperature, heat will stop being transferred from outside into the block because they are the same temperature. When we continue heating, when its temperature is above room temperature, heat will move from the block to the surrounding air because the block is warmer. And when the temperature reaches 10 degrees above room temperature, we stop timing. Now the amount of heat the block absorbs when it is cooler than room temperature will be equal to the amount of heat it loses when it is hotter than room temperature. So these two cancel out. The amount of heat it has absorbed and the amount of heat it has lost to the surroundings will cancel out. And then we can use our formula C is equal to VIT over m delta theta. So this is how we eliminate heat losses or heat absorbed from the surroundings. The same method can be applied to find the specific heat capacity of a liquid. So in the calorimeter, we place the liquid with an electrical heater. A voltmeter measures the voltage across the heater, an ammeter gives the current. We have a thermometer to give the temperature of the liquid, and a stirrer because we need to stir the liquid so that its temperature is uniformly distributed. And then again, energy supplied is VIT, and C is equal to VIT over m delta theta. And to account for heat lost or heat absorbed from the surroundings, we cool the liquid, for example 10 degrees below room temperature, and then we heat it until it is 10 degrees above room temperature. And we note the time taken, and we use this formula to find the specific heat capacity. Now there's another quantity called the heat capacity of a body. The heat capacity, capital C, of a body is the amount of heat energy Q required to raise the temperature of the body by 1 Kelvin or 1 degree Celsius. So for example, suppose we have 20,000 joules of energy is required to raise the temperature of a chair by 2 Kelvin. Calculate the heat capacity of the chair. So when we calculate heat capacity, the mass of the body is not important because we are calculating how much heat is required to raise the temperature of the body as a whole by 1 degree. So if 2 Kelvin requires 20,000 joule, so 1 Kelvin requires 20,000 joule divided by 2, that's 10,000 joules of heat energy. So the heat capacity of the chair is 10,000 joules per Kelvin. In other words, to raise the temperature of the chair by 1 Kelvin or 1 degree Celsius, we need 10,000 joules of energy. So we see that mass is not into the equation here. To calculate heat capacity, we use energy supplied divided by change in temperature. So in other words, heat capacity is Q over delta theta. And its unit is joule per Kelvin. Here's an example. A block of aluminium has a mass of 10 kilograms. When 270,000 joules of heat energy is supplied to the aluminium block, its temperature rises by 30 degrees Celsius. Calculate the specific heat capacity of aluminium and the heat capacity of the aluminium block. So the specific heat capacity, we use this equation, Q over m delta theta. Energy supplied is 270,000 joule. Mass of aluminium block is 10 kilograms and change in temperature is 30 Kelvin. And the specific heat capacity is 900 joule per kilogram Kelvin. Now we need to find the heat capacity of the aluminium block. So you will notice that when we talk about heat capacity, it is for a body as a whole, not for the substance. Just like the chair in the previous example, the chair had different substances in it. We look for the heat capacity of the chair as a whole. Here we look for the heat capacity of the aluminium block. So we don't have to take into account its mass, because 270,000 joule of heat energy will raise the block's temperature by 30 Kelvin. So to raise it by 1 Kelvin, 270,000 joule divided by 30. You get 9,000 joule per Kelvin. So this is the heat capacity of the block. You need 9,000 joule to raise its temperature by 1 Kelvin. So the formula is heat capacity is Q over delta theta. Now if you compare these two equations, you can see that the mass is not present in the formula for heat capacity. So if you multiply specific heat capacity by mass, you get heat capacity. Because if you multiply this equation by m will cancel, you get Q over delta theta. So heat capacity C is equal to mass times specific heat capacity.